just have been on Zoom.
I used to just wonder.
No, I'm just, I'm really on it. It was like, I'm just it's not so good.
Hybrid car.
Yeah. I was sitting here, that thing's my result.
You guys have.
Oh, you guys ready for profiling? Yeah. Okay. So Austin talked this morning about some of the acoustically based instruments that we use to measure velocity and turbulence and quantities related to turbulence. And I'm going to talk about profilers. And a lot of the same sensors are also used on like profilers that we throw off of ships, which is mostly what I'm going to talk about. And also floats use some of the same stuff, and gliders are now starting to use some of the same instruments. So yeah, the Microstructure family of products. So we're going to talk about how to compute epsilon and chi spectrally, platforms and sensors that we use for measuring microstructure, the relationship between epsilon and chi, which we've already touched on a bit, but like specifically how it relates to observing these quantities with instrumentation, and a data example if we have time. So a little bit of a review. So epsilon, the rate at which kinetic energy is dissipated, chi, the rate at which temperature gradients are dissipated. If you knew nothing about how these things are observed, if you just wanted to measure the rate at which kinetic, oh, did I sign back? So I just heard an echo. Am I crazy? No. Okay. We're good. All right. So yeah, if you just wanted to know the rate at which kinetic energy is going away, and you could measure any quantity that you wanted to, you weren't limited by instrumentation, how would you go about measuring that? Maybe this is too open-ended of a question, but I kind of wanted to get us to think creatively about it.
You need a rate, so you just take a lot of like high frequency and time measurements, and you can just say like after X seconds it decrease this much, and it'll just be your rate.
Yeah, totally. If we were completely unlimited at the scales and time and spatial scales that we were able to observe it, I think that probably would be the best way. So Em said that if we could just take really closely spaced measurements in time of our temperature gradients or of our velocities and see after a certain amount of time when they go away. But can anybody think of like, I don't know how you know what I was thinking. What I was thinking is that you would also have to control the rate at which the temperature gradients, like the forcing on them. So you would have to know how is kinetic energy being added to this box of fluid that you're interested in, or are there forcings that are influencing the temperature gradient other than dissipation, right? Because dissipation is only one side of the equation. And then you have thermal energy exchange and you have kinetic energy coming into the box. So how we work around this is we try to use our knowledge of fluid mechanics and our knowledge of the energy cascade that we've been sort of building up over the past couple days to help us determine epsilon and chi using spectrum. So if we can Fourier decompose our data, we can see the amount of energy that is at those small scales, even if we're also observing stuff at larger scales. And that is what allows us to sort of try to separate the forcing from the dissipation and target in on those small scales that we're interested in. So these dudes' names are what we call the theoretical spectra that we're going to be using. So for the shear spectrum, there's a couple different flavors. There's Panchev and there's Naismith, and they're not that different. I think in our processing code, we use the Naismith spectrum. But Arnaud and Nicole are going to do a super deep dive into like exactly how to compute epsilon and chi in week 3. So today I'm going to do sort of a larger overview of it, and hopefully that will set you up well to learn more from them in week 3. And if you forget anything, they'll cover it again, or if I gloss over anything or get anything wrong, they will fix that. Yeah, and so then the bachelor spectrum is for temperature gradient. So the thing that allows us to, what we really are interested in are spatial gradients, right? We're interested in the vertical gradients because we've assumed that the horizontal gradients don't matter, or the vertical gradients are what's most important, or whatever. So for chi, we have this, where's power? We have this vertical gradient of temperature, and we want to know the variance of the spatial gradient. But now we're gonna try to use a spectrum to talk about the quantity of variance in a spatial parameter. So do you guys remember, did anybody raise your hand if Parsifal's theorem rings any kind of a bell to you? If you took data 1, I might have been your TA. Okay, so Parsifal's theorem basically tells us that the variance of any quantity in the time domain or the space domain, whatever domain you're spectruming in, is equal to its variance. So in time, it's equal to the frequency domain. The analog to that would be in a spatial, the variance in a spatial domain is equal to the variance in the wave number domain. So if you Fourier transform your thing and you split it up into different spatial scales or different frequency scales, the variance of that quantity should be the same. So that's what allows us to get from this guy to this guy. So the integral of the spectrum equals the variance of the temperature gradient in space. We can do a similar thing for epsilon. So we have this spatial variance of shear in the vertical, and Parsifal's theorem allows us to say that that is equal to the integral of the spectrum plus all these constants that stay on the outside.
Sorry, what
Yeah.
was in the first equation, the one before that, psi? What is that representing?
That's just the spectrum of the temperature gradient spectrum. It's just like we're using that to equal that shape that is the spectrum.
Why have you changed the D to kappa?
Because I totally just pulled these from 2 papers that are different,
But
that have different notation, but those are the same.
There's
So that's the eddy diffusivity of temperature.
I know.
Is it molecular? Okay,
It's not.
Akita says it's molecular. Thank you, Akita. Okay, so now we have this profiler that is dropping, free falling, if it's an epsilometer, through our fluid. And we are saying that the integral of the spectrum is going to be equal to a spatial derivative. But in reality, what we have is an observation that's varying in space and in time. So we have to make some assumptions to equate that to a pure spatial derivative and then use Parsifal's theorem and get the spectrum and make all that valid. So this Taylor guy had this theory that if you just assume that you have a snapshot and that you are profiling through a thing that is not changing in time, then we can use the fall rate of the instrument to equate what we have to a spatial derivative. Does that make any sense? So like, if this field wasn't changing in time and we're just falling through it and we know our fall rate, we can say that even though this is varying in time, we're going to ignore the part that's varying in time and say that we just have a spatial derivative. So that's an assumption that we're making. And that assumption is pretty valid because when the windows that we use to make the spectrum from the epsilometer are like 2 to 3 seconds. I don't remember the exact value, but I know will leave for you if you care. So in order to make this assumption, we have to assume that the turbulence is steady so that it's not changing, at least statistically, in time. And we also make this isotropy assumption that we've mentioned, we've been harping on all week, that the direction that you measure in doesn't matter. So that means that if you have a profiler that's dropping vertically, or if you have a glider that's coming through horizontally, or some other angle, that is not going to change the turbulence estimate that you get. And we've also assumed this thing called self-similarity, which is that the flow structures are similar at different scales. So like all the scales that are captured within your shear spectrum that you're looking at, the little eddies that you're measuring are similar at all those scales. Yeah, so these are some of the instruments that we use, specific to the mod lab. This guy is the fast CTD, so he falls at like 6 meters per second or less. And we have a really high speed winch that we use to like let the line out that fast and then yank it up really fast. And the speed there is just to get a higher spatial resolution. And so we get about 0.5 meter of depth resolution. And the pointy end of this guy has a thermistor on it, which you can see a zoomed in version of right here. The way this guy works, like the sensor that's actually at the very pointy end of this probe, is a thermistor. Does anybody know how a thermistor works or where that word comes from? Austin. Was that a hand? You can answer. No? Okay. Nobody wants to guess? What was that?
Vibrates, it's something that vibrates.
There is a vibrating instrument, but this is not the one.
Oh,
So a thermistor is measuring temperature.
No. Like with electricity, I think, like with that current. but
Yes.
I don't know exactly how it works, yeah.
So, yes,
Yeah, so it's like you have two different bits of metal that are poking together at any given time. And the temperature differential across that creates or induces a voltage across those two different metals. So it's tuned to whatever they are. And then that signal goes into like a whole circuit thing that we and then measure that voltage and get the actual temperature at the tip.
so a thermistor, the word is like resistor, but temperature. So like a basic property of anything metal is that as you change the temperature of it, that causes the molecules to vibrate at different rates. So a hotter metal, molecules vibrate more, the metal expands slightly, and the resistance drops. So hotter metal, high resistance, colder metal, low resistance. If you measure the resistance of this probe tip, then you can track the temperature. So that's kind of what's in the guts of a thermistor. And then this guy is, we call it the epsilometer. It has this little parachute that opens up so that it falls at a set rate. And the reason why we have to go slower with this one is that it has a thermistor on it, but it also has this guy, the white, I don't know, silicone one, and that's a shear probe. And I'm gonna go a little bit more into depth about how shear probes work because you'll get to see what's inside of one later, and I want you to know what you're looking at. So hold on to that one, but that's why we have to fall at a set rate. And then this is a kind of new one that's like come into being during my tenure here as a student. I worked on it as a first year, but it's never been my baby. But it's an acoustic sensor, kind of like what Austin was talking about. So this little circular dude right here is the same as the circles that were on the ADCP in that it's an acoustic chip and it vibrates really quickly and sends a pulse into the water. And that is like the sound wave that's coming out. And on the opposite end, there's another one of these and they talk to each other. And so based on the time that that signal takes to go back and forth. So if you have one chip and another one, this one sends out a signal and you know how far apart they are and you know the frequency of this signal, so you know how long it should take to get there. If there was a flow velocity going this way, going with the direction of the signal, it would get there just slightly faster. And so based on the time that it takes from the signal to get from one side to the other, you know the velocity, the average velocity of the fluid between these 2 points. And so one of the cool things about this geometry is that we can pick whatever distance we want between those two. And it's kind of like the ADV in that it gives you a point estimate, but it's an average of the whole volume between these two sensors. So we've picked a really small distance because we're interested in turbulence scales. But if you wanted to, you could have an array of different sizes and get an array of different scales. Yeah, so that's the TTV. And all three of these can be on the end of the epsilometer. We'll have a smaller version of this that goes on a fishing reel. So instead of having this cable, it transmits data live back to the ship. So like as you're profiling, you can see what you're measuring, which is really cool. You guys will not have that. You will have a rope. And you'll have an independent package that you have to bring it back up to the ship and take the data off like an SD card to see it. And it'll be a smaller version that you'll get to see later today. And you won't have a TTV, but you'll have a thermistor and a shear probe.
Wait, so,
Yeah.
a thermistor is a type of CTD? Is
The
that,
thermistor just gives you temperature.
okay,
So just the T in CTV.
CDD is
oh,
conductivity, temperature, depth.
yeah, but I'm just saying like, so, but because you're measuring resistance, not just like any form of electricity, okay. So it's just, okay,
So you're just getting temperature, but there is also a CTD on board the epsilometer. So you will have a Seabird CTD giving you conductivity, temperature, and depth at a slightly lower resolution. And then you'll also have these probes measuring temperature at a much higher resolution. So your chi, your dissipation of temperature gradients, will come from this guy, but you'll also have temperature data from the CTD, which is on board. Yeah, Kaiki?
I would just like to add that some of the new facilities, they have this new microconductivity, probe. That will end up also measuring just mostly temperature fluctuations. They're doing Kai from that too.
Right. I'm pretty sure that's what this is.
Oh.
So it's a,
Wait, did you say microconductors? Do you mean the measure salinity?
Yeah, but also, also temperature.
yeah, so we're assuming that the only thing that's impacting the conductivity is, maybe I have it wrong then. Maybe that is a micro, FPO7 is that microconductivity or thermistor?
It's
Okay. Okay, so that is an FPO7. This one is only measuring temperature. Maybe I don't have a picture of the microconductivity. I think what you were describing earlier is the microconductivity probe with the two different metals. And it's measuring the conductivity of seawater between them. And then the conductivity of seawater depends both on temperature and salinity. But we usually assume that the salinity is negligible. Yeah,
Could you explain again why the sinometer has to fall like at a slower rate than the capacity?
yes, but I will wait till my next slide
Oh, okay.
because that's
Sorry.
what it's about. No, it's good. Yeah, Austin?
Kind of related to that, the sampling frequency of 320 hertz, the 1 meter depth of resolution, is that because you're like averaging? Because like, it's a higher like sampling rate, but
Right.
are you just averaging over a meter, or is it like?
So you're falling slower and you're taking something like 2 seconds of data, and I'm not 100% confident on that, but you're taking something like 2 seconds of data and making a spectrum. So it's not like at every single of those 320 hertz points you have an estimate. You need to take the shear and the temperature gradients that you measure from these probes and then make a spectrum. From that spectrum, you get estimates of chi and epsilon.
It is also bent to 1 meter, but
Yes.
you're right. I think that's a choice because of the resolution of the data as well.
So the choice of the bin depends upon the scales that you want to be measuring in your spectrum to get a good fit. But we'll get to more of that later. Okay. So I'm gonna get a little bit deeper into what is inside of a shear probe because I think it's cool, it's what I study, and because you'll get to look at one later and I want you to know what you're looking at. So stepping backwards a little bit to why an ADCP and a shear probe work, they're actually made of the same type of material. It's called a piezoelectric material. And so when a piezoelectric material experiences any kind of a mechanical deformation, you get a voltage response out of it. And it also goes the other way. So the way that an ADCP works is that you have this little circular disc, which is made of a crystalline material that has this piezoelectric property. And when you send a voltage to that piezoelectric material, it vibrates. And that vibration pushes on the water and creates a sound wave. So that's what makes the ADCP produce sound. And a shear probe works in the opposite way. So we're trying to measure the fluid motion at very small scales. And when the water pushes on the shear probe, because you have a fluctuation in velocity, that mechanical deformation will produce a voltage response. And so that property of material is called piezoelectricity. There's also ferroelectric materials, which in response to a temperature change will give you a voltage response. Or maybe that's pyroelectric. I forget what ferroelectric is. Yeah, and most piezoelectric materials also have a pyroelectric response. And if they're too sensitive, you have to adjust for the temperature change, but that's way too in the weeds. Okay, so you have a piezoelectric material, and the thing that determines the axis that you're measuring, so the sensitive axis, is polarization. So by subjecting this material to a very strong electric field, you can determine how the molecules are oriented. And that is why it's called polarization, because you want the molecules all to be rotated in the same way. And it's defined based on the axes of the material. So if you have like the 3, 2, and 1 axes, for example, the way an ADCP is oriented is that you apply a voltage across the 3 axis and you want a deformation in that same axis. So if you picture having this cylinder and you want a sound wave to come straight out the face of that cylinder, it's polarized so that they apply a voltage across both sides of the face, and then that is the same face that pushes on the water. The way the shear probe works is that it's 3-1 polarized. So you measure the voltage across the three face, and you want to be sensing a deformation in the one axis. So it's configured in this way that's called a bimorph, which is sensitive to bending, but insensitive to a normal force. So the shear probe actually has two piezoelectric plates that are oppositely aligned. So if you just take one of those, if you just look at the top one and you stretch it and you measure across the top and the bottom, the stretching of this will give you a voltage response. And then you take the plate on the bottom and you flip it in the opposite direction, so that if you just push on the front of the shear probe, the voltages cancel each other out. So you get -1, +1. But if you bend it, then you have stretching on one end and squishing on the other end. So you get the opposite response, you get +2 volts. Does that make sense? Questions? Concerns? You want to stare at it for a little longer? Yeah.
Are the voltages like binary? I assume there's like, you can have like 0.3 and like -0.4, or is it just +1, -1?
So ideally you want them to be equal and opposite. But there could be some imperfection in the material, or I think any bending moment, as long as the thing is actually axially symmetric and these two plates are identical and opposite, should produce equal and opposite results. I have a hard time thinking of a geometry that would not do that. You would have to have a bending moment that was on an axis that was off center.
So pretty much everything will show up as either 2 or 0.
Yeah, yeah. And the idea of that is that as your profiler is dropping through the water, you're really looking to measure the shear, which is du dz. So maybe that is better to look at this diagram. So the way that this bimorph works, so we're sensitive to bending moment. If this is the shape of the probe, we are measuring the lift force on the outside of this. So kind of the same way an airplane wing works, the fluid flowing over the shape is going to create pressure gradients, which can be measured as like the same. This is labeled as an L because it's the same math that gives you lift that lifts up an airplane. So because of the differential pressure gradient on so if you have a slight angle in your fluid, there's going to be higher pressure on this side and lower pressure on that side. Yeah. So that is what allows you to, that's what creates the bending moment. And then because we know, we have a lot of theory that helps us predict the pressure gradient that would result from a specific angle of attack. From that angle, we can back out this tiny component of U, which is what we're interested in. So as the probe is wrapping through the water, we're measuring the changes in the horizontal component of velocity, which is du dz. And we're doing it on a scale that is, we assume at least 4 times larger than this shear probe. So it can't measure things that are smaller than itself, but it can measure things that are at least 4 times bigger than its own diameter. Yeah, so instantaneous lift force is equal to this this coefficient, which is just a linear coefficient that relates the angle of attack, this angle, to the lift force that you're going to get, lift coefficient, CL. And then this is called dynamic pressure. So it equals this, which is related to the rate that you're falling, the density of the fluid. Area is just an effective area of like, what exactly is the fluid pushing on? How big is the outside of the probe? And then this is the ratio of your total fall speed to the tiny component of U that you're trying to measure. So same math as you would do if you were trying to fly an airplane, or maybe not while you're flying, but like designing it. So if you assume a small angle of attack and spatial scales of turbulence that are much greater than the foil diameter, so that's where the 4 times bigger comes in, you can simplify this equation to be just in terms of the dynamic pressure and the fall speed. And so then how we do this with actual probes is we calibrate them. So what you guys are gonna see later, is a tank that we use that creates a very laminar jet of flow. And we take our probe and rotate it through a small angle of attack. And that way we get an electrical signal and a sensitivity constant. So what we're measuring for is this constant that will allow us to translate between the signal we get and the angle of attack. And this is theoretically supposed to be a linear relationship, and it is pretty close to one. But for every single probe that we make, we run it through the calibration tank, because based upon like the microscopic structure of the piezo material, this sensitivity constant will be different for each probe. So that's why we have to calibrate them.
You only have to calibrate it once during its lifetime, or?
We only calibrate it once during its lifetime, but as somebody who manufactures shear probes, I have seen their capacitance, which is a measure of their related to their sensitivity, change over time. So ideally, what I would prefer is to create some sort of an in situ calibration jig that you could bring on the boat with you and calibrate right before you profile. That would be better. But what we currently do is calibrate them once. Good question. Yes.
Maybe you mentioned this before, but with the airfoil probe, are you only measuring shear in one direction per probe? And then would you need multiple probes all like facing as many angles as you want?
Thank you. I should have said that. Yeah, so because we have this configuration where we're sensitive to this is like a sandwich, so you have like two layers of piezo material that are sandwiched together, and it's sensitive to bending along this axis, but not this axis. So we'll see that in the demo later, like we'll test each one. But yeah, we are only measuring one direction of shear, and that is another reason why we assume, or why it's convenient that we already assumed isotropy in our theory. Even if we did measure two directions, because the theory that we're using to get epsilon and the way we understand epsilon, like as scientists, we don't even know what to do with two directions of epsilon. That would be cool. What we usually do is put two shear probes next to each other and rotate them just for fun, but it's more for like in case one breaks, or to compare the two measurements, or you can average between them. So we do actually usually have two, but not because we're actually thinking about the two different components very much. Yeah.
The results of the both of them are too different, because I find the two of them are measurement different, but they are not that far. So I understand that in case on one doesn't work, you're using the another one, but the difference between them are, I don't know, they are pretty similar to this curve.
So because we are actually only able to resolve things that are minimum of 4 times greater than the diameter of the probe, if we had stuff that was varying on smaller scales than that, our probe wouldn't even be able to resolve it anyway. And they're pretty close together on the instrument. So I think that we're actually at just about this length scale apart.
Not
Yeah.
that different.
Yeah.
Okay.
Good question. Yeah, Nikita?
Could you explain what the foil diameter is? So are you comparing like this length, or are you comparing like how?
Yeah,
Right.
so it's this diameter of the probe.
Okay.
So because we're only sensitive to one direction, even though the probe itself is round, the effective area, like the lift force, is kind of like, you could almost imagine it as a 2-dimensional airfoil. I don't know if that helps at all. But yeah, it's the like radius around this, or the diameter around the probe.
And so your piezoelectric is like the diameter of that foil, and then you kind of trying to figure out how much it's shifting with that voltage difference, right?
Yeah, so like I should have included a slide on this, because I did a whole model about like, so as the fluid is passing over the silicone, which is the outside skin of this probe, it is exerting a pressure on that skin. And then that pressure is translated through the material and creates a bending stress inside of the material. So now I wish I had the slide. So if you think, let me just draw it. So if you have a probe that looks like this, and there's pressure exerted on the skin on the outside of it, and you have some piezo that's in here. I don't know if any of you engineers did like beam bending problems in any of your classes. Yes, I'm seeing 3 nods. Okay, so if you picture yourself on a diving board, all right, and you're jumping on the end of the diving board, the biggest bending stress, so like the thing that we're measuring is the bending, is going to be at the end that's attached to the pool deck. So like the force that's exerted on the outside of the airfoil does something like this. So the most force is exerted on the end of it by the lift distribution of pressure. But because it's effectively a cantilevered beam, only 3 people, only a handful of people in the room know what that means, but picture it as like a diving board that somebody's jumping on, okay? And the bending stress is actually greatest at this end of it. I don't remember what the original question was. We were talking about what it is that we're actually measuring.
I guess I'm just trying to visualize your diagram from before with the airfoil, but I think
Okay.
this helps.
This
Yeah,
helps.
This makes sense.
Good, good. Yeah, so we're trying to measure so like if you picture the diving board again and you're pushing on it, you're stretching this one and you're squishing this one. So like if you're pushing right here, this piezo is being slightly stretched and this one is being slightly squished because the whole beam is just being pressured that way. And so depending on how far you are from the pressure that's on the skin of this, ideally the greatest like stretching and squishing you would get is if your piezo was all the way on either end. But because the crystals are just like rectangles, they're just sandwiched right in the middle of it. But I'm working on a different geometry that I'll show you later and I won't stress you out right now. Yeah, Katie?
And sorry, just to clarify, so you measure the lift and from the lift you get the velocity. And then you compute shear with the gradient. You don't directly measure shear, right?
So we are measuring this voltage and then we use this sensitivity constant to get the component of velocity. I'm just trying to think. It's kind of a strain rate. So I think maybe it is a direct measurement of shear, but regardless, what the calibration constant is giving us is the angle of attack of the flow. So like what we relate our voltage to is the angle that the probe is making in the flow. And that's what allows us to back out this component. So I do think we still need the fall rate to get shear. Grant?
The airfoil probe and the shear probe are different probes.
Same thing. It's called an airfoil probe because it was invented by aerodynamics people who were trying to measure turbulence in a wind tunnel. And because the shape of it is airfoil shaped.
So the airfoil probe is measuring velocity from lift.
They're both measuring shear.
There's-
It's the same thing.
Yeah, but there's the shear probe which is within the airfoil probe, which is the same thing, is also measuring its velocity separately via piezoelectrics.
A shear probe is the same thing as an airfoil probe. Sorry, that was confusing to switch to the word airfoil. It's airfoil just describes the shape of this thing, but like this is the same probe that is attached to an epsilometer and it's a shear probe.
It's a drawing that Charlotte has on the board there. It's like that piezoelectric crystal that was on the previous slide.
Yeah.
That is what's encased in a silicone that looks like a little bit of a paintbrush. If you go back to the other side, I think you have a picture of it on the. Oh, yeah, it's that white paintbrush.
So inside of this silicone is 2 piezoelectric crystals glued together.
And they're measuring the lift force.
Effectively, yeah.
Okay, I thought the velocity was deforming them directly.
So the velocity is deforming them, but the velocity is pushing on the outside of this probe. And based on the pressure force on the probe, we can extrapolate the velocity because we know that there's a linear relationship between lift force and angle of attack at small angles.
Okay.
So like you're right, the velocity changes are pushing on the probe.
Yeah.
But the thing that they're changing is the pressure distribution on the outside of the skin. That's why we have this shape of the silicone, right? Because otherwise we could just have a rectangle or some simpler thing. Yeah.
How precisely can you know the fall rate?
I think we're measuring it directly?
You can do multiple ways, so you don't really see it on this picture of the FC, but if you look at the stickers that we made for you. That blue thing sort of is like a little fan thing that folds out, you'll see that on the boat later. So that sort of is a little parachute to slow it down, so it's not going super fast. There are multiple ways we can add lead, we can add foam, we can do a bunch of things to balance out to try to achieve that fall rate. There are pool tests before, so we roughly know. But then there's things such as like, currents, how salty the water is, like what's the density where we're at, like there's a bunch of factors there. So the fall rate is rarely an exact science, but like Charlotte said, there is a CTD that goes along with this FC, right? And the CTD gives you conductivity, salinity, temperature, and depth. So that one can tell you like how fast you're falling just from how your pressure changes. So we aim for a fall rate of 0.65 because that's when the instrument operates best. But there is a little bit of leeway and there's some finagling and trying to get there, and we don't always hit that perfectly.
Going off of like the fall rate, is there a reason why you're not just like using a like higher power winch for that? Like, does it need to be in free fall for it to work properly?
Yes, it does need to be in free fall. So, yeah, so we use the same high-speed winch that we use for the FCTD, or in the case of you guys, you're gonna be using a fishing reel. But one thing that you'll learn when you're profiling is that like you wanna be watching the line as it's going into the water, and if it goes taut, then it's tugging on the top of the instrument and it's no longer in free fall, so that data is gonna be bad. So you need to make sure you're letting out line fast enough that it's not affecting the instrument. Camilla's smiling because you stared at this line going into the water for hours.
Yeah, because then you get knots when it way up.
Yeah, right. And if you let out too much line, then you'll get knots. So it's a delicate dance.
Yeah, the idea of keeping it in free fall is to try to make the movement of the ship kind of independent from the falling of the instrument. So it's just a way to minimize that error, which can be quite big in some of these instruments.
Real quickly, you're always stationary when deploying these, right?
We do transect sometimes. So the ship will be moving. The profile will be stationary, so we're letting it free fall and we're not dragging it. But then while it's coming up, we are moving to a different location.
Okay, so you're letting out line both for it going down, so because you're away from it.
Uh-huh.
Sounds fun.
It is, yeah, it's great.
You will experience it
And
next week.
this guy is talking to the ship live, so we actually, if you're using this version, which you won't be, you are getting live fall rate. So it'll say on your little iPad display what the fall rate of the instrument is, which is super cool, but you guys aren't gonna have that. Sorry. Yeah. Yes.
I'm so sorry if you're.
This is great. I will skip other stuff later on that's less fun.
Why is there the order of magnitude difference between the fall rates?
Because of the shear probe. So this only works if you're falling kind of slow. Because you're using this relationship of like you have this U fall is very tuned to the instrument, and it doesn't work at faster speeds. But the other one just has a microconductivity or a fast thermistor, so it can fall as fast as it wants. Okay. Shall we move on? Oh yeah, and this is just shear probes are really old. This Sidon guy in 1971 was in a wind tunnel, which is why it's called an airfoil probe. Also, the shape of the probe was invented by aerodynamics people. And then this Osborne guy adopted it to use in the ocean. And that's really the same thing that we're still doing now. Except for the one I'll show you later is a new material that is the active sensor. So that's the first change that has happened, other than like minor geometry tweaks. Okay, so as you are making this profile, this is what a profile of epsilon or chi could look like, and each one of these little estimates is made from a spectrum from our instrument that comes from like 2 or 3 seconds of data. So this is the theoretical spectrum for epsilon, which I think we've looked at a couple times this week already. This is the Naismith flavor. It's only a function of epsilon. So the different colors are what the Naismith spectrum would look like for different values of epsilon. The darkest one at the top is a higher energy level, more epsilon. This is one spectrum, one data point from a shear probe on top of that from the epsilometer. And this has the instrument noise added on top of it. So like that big tail where it hops up at the end is electronics from the instrument and noise that's associated with the platform itself. So that determines really the smallest scales that you can measure on your spectrum. So does anyone want to take a stab at guessing what value of epsilon we're looking at here?
And then it would be.
Yeah. Pretty good. Yeah, so Arnaud will go more in depth and Nicole on like all of the stuff that is behind that estimate, but this is the basic idea that based on the level of the spectrum, you fit the Naismith spectrum to that, and that gives you epsilon. Pretty simple.
Sorry, what is the dotted line?
That's the noise.
Oh,
So
okay,
like,
that's the dotted.
yeah, noise is really coming into effect at these higher wave numbers. And so that's why the signal jumps up there at the end.
So where the Naismith spectrum and the noise line like meet, that's like the highest, the smallest scale you're looking at.
Yeah, so that's where when we integrate the spectrum, that's where we cut off, because we
Okay.
don't want to integrate all that noise. Kaylee?
Oh. Alright, but, it seems like you are. I think you can see when it turns into noise, but it also setting it. How are you estimating?
So we run the instrument on the bench, not in the ocean, for a very long time, and that gives us an idea of what the noise floor for that instrument is. And also the noise follows a theoretical shape, which is this shape, that is determined in the lab. So I think that and I'm not an expert on this, maybe Ankita knows more, but I think that they fit this theoretical noise spectrum to the high end of the spectrum to get an exact estimate of where this cutoff is. So they do like, you're doing a best fit to the Panchev spectrum to estimate epsilon, but you're also doing a best fit to the noise spectrum to figure out where the cutoff is.
Yeah, they kind of like do some kind of scaling to get to remove the noise, and so that you can compare all of those spectra together. But yeah.
Yes.
So wait, so the Naismith spectrum is just his derivation of what these should look like.
Yeah.
That's okay. So I wasn't sure if there was like a different way we were calculating spectrum. Same way, just okay.
This is a theoretical shape that is a function of epsilon. Which I didn't put the equation for because it's long and boring and nobody cares. Okay. This is for chi. So this is the bachelor spectrum. The bachelor spectrum is a function of epsilon and chi. So for this particular plot, I have set epsilon equal to 2 times 10 to the negative 8 because that is the same, it's going to be the same data point from the epsilometer that we were looking at earlier. So this measurement is from a shear probe, and the one that we're going to add on to it is from the FP07. So we already know what epsilon is. And this is all the different values of the bachelor spectrum we could get with that epsilon, and we're going to try to figure out what chi is. There's the noise. Anybody want to guess what chi is from this? Not a trick question. Close. 2 to the negative 6. Yes.
And that is like I don't know, by an eye. Like
So-
okay, it's not, we cannot do like a meeting or something like that to see what is more close to -6 or -5.
So we're just eyeballing right now to show you that this fitting thing is kind of legit, but what the code does, and Arnaud and Nicole will get deeper into this, is actually integrates the data spectrum out to a cutoff that is based on where the noise is.
Okay.
What if we didn't know what epsilon was? What if we were using the fast CTD and all we had was this data, which I guess kind of looks like a bachelor spectrum, but because the bachelor spectrum is a function of epsilon and chi, this is kind of unconstrained. Like these are, so if you set chi to 2 times 10 to the negative 6 and you vary epsilon, like look at all these different epsilons that you could get and different chi's that would correspond to integrating these theoretical bachelor spectra. So in that case, which we only have 10 minutes left, so I'm just gonna maybe speed up a little bit. We can use the relationship between epsilon and chi in the case where we're only measuring chi to get a better estimate. Like kind of the worst case scenario would be if we just say like, you know what? We're measuring temperature variance. We know we need to integrate the spectrum. We can see where the noise is. Let's just integrate out to the noise and call that like the best case. But depending which one of these bachelor spectra actually corresponds to the like fluid dynamics, you're either resolving all of it, if it was this case, or you're resolving much less of the spectrum if you have a higher value of epsilon. And so you don't really know how much you're under resolving chi unless you can get an estimate of epsilon. So we can use the relationship between epsilon and chi. So like the only case in which there is a relationship between epsilon and chi, or where that relationship is complete and describes everything that's going on, is if you have mechanical turbulence, so that's epsilon, and you're mixing away density gradients that are determined by temperature. So in that case, there's this direct and complete relationship between epsilon and chi. And if you know the efficiency of the mixing, so that's how much of the mechanical turbulence is dissipating energy and converting it to heat versus how much of it is going to changing the density gradient, so that is creating potential energy. Okay, so here are these eddy diffusivities that I think we've looked at a couple times so far this week. So this is just describing like, the first one is temperature eddy diffusivity. So this is assuming isotropic turbulence and assuming that only the vertical temperature gradients, well, I guess that's kind of the same thing, assuming that we only have a vertical temperature gradient and thus the isotropy assumption is valid. We can get this temperature eddy diffusivity. This eddy diffusivity is making different assumptions. So this is assuming that there's a balance between shear production, buoyancy production, and dissipation, and also that we are in steady state and that the mixing efficiency, so that's the rate of kinetic energy dissipation that's going into producing potential energy, right? So assuming that that's constant, a lot of assumptions. That gives us the ability to write this eddy diffusivity of density in terms of epsilon. Okay, so try to absorb all of these assumptions because we're going to come back to them in a little bit, or at least remember one of them. Everybody remember a different one. Okay, so we've made all those assumptions. We can write these eddy diffusivities in terms of epsilon and chi. If we assume that salinity is unimportant, or if we're in a case where we can show that that is true, which is true for some of the ocean, but for example, in polar oceans, a lot of times they're salinity stratified, or other salinity stratified places like the Bay of Bengal. This is not a valid assumption. So there's a lot of places where this isn't valid. But when it is, we can write epsilon in terms of chi, because we can just set these equal to each other, solve for epsilon, and then we get this guy, which is epsilon in terms of chi. Great. So we've started with only chi data from our FastETD, and we can compute an epsilon in terms of chi, assuming all of that stuff was valid. Now, what I was trying to show earlier with like the noise and the spectrum moving, there's this is a bachelor spectrum, and this we can imagine is where the noise of our probe starts. So in different Reynolds number flows, we're resolving, if we can only integrate out to this probe resolution, in this case, we're resolving a higher percentage of the variance of the spectrum than in this case. So if we integrate all these up to the probe resolution, we can create this power law relationship between, if chi is a constant, there's a power law relationship between epsilon and the R, which is the ratio of resolved variance. So the amount of variance that we're resolving depends upon epsilon if chi is constant. And we know chi from our direct observations. Okay. So if all of this is true, we can fully constrain our bachelor spectrum with epsilon and chi, and we know how much of it we're resolving. So if we want, we can integrate the theoretical spectrum all the way out to the end and get the total value of chi. And then we have also computed epsilon from chi. So this is constrained. Okay. Let's shake all of that off and look at some data, just to leave you on a fun note before lunch. So this is a cross-section of the Gulf Stream made with the FCTD. This is like there's warm water over here and there's cold water over here. And this is the part of the Gulf Stream that splits off from the coast, waves around like a garden hose. And so we have this water mass we call the Sargasso Sea, this water mass we call the Slope Sea, but generally we have cold, fresh, salty, warm. And we have this 2 meter per second current that's like a jet that's separating them. So that's sort of what this depiction of the Gulf Stream is showing. Where do we expect epsilon to be high?
Scissor maybe?
Where the two water,
Yeah, where the closer the two water masses.
what is it like about what is it about that you would expect epsilon to be high, I guess?
Strong.
Epsilon in particular. Okay, strong shear. Yeah, so it's like related to where the current is strong?
Yeah.
Anybody want to add anything in terms of epsilon or chi? Where would you expect chi to be strong?
Higher between the two temperature gradients, right?
Yeah. So where there's a stronger temperature gradient? Cool. Anywhere where you would expect them, I guess, where would you expect both to be high?
The intersection between the edge of the jet and the temperature gradient.
Yeah, so like you need a temperature gradient and a strong velocity signal to get high epsilon and high chi, right?
What are the white lines?
Oh, those are isopycnal, sorry. So that's lines of constant density. Does anybody see any places where those assumptions are violated?
Around the current. It's a current. So in the H where the isopycnals go close each other. Because the gradient is stronger there and also the change of current.
What's the assumption that's violated?
I think we're not assuming in certain regions, there's not only vertical gradients. In temperature, for example, there are
That's
also
a good-
horizontal gradients.
Yeah, so.
Yeah, like
horizontal-
above 100 meters more to the, I don't know what the x-axis is. Latitude or something.
Yeah, sorry, this is like 200 kilometer
Oh, okay,
section. Or no, sorry, 30 kilometer section.
okay, yeah, like
So
the
200.
farther into the section. There's also horizontal gradients in temperature, for example.
Mhm.
It's pretty strong.
Yeah, so like if you follow this isopycnal with your eye, you can see that the temperature is changing along the isopycnal. So that means that density is changing even though temperature is remaining constant. So that tells us that
That's true.
salinity is important. Okay. I'll flip to the answers and then we can talk about some of the patterns that we see. Does anybody notice anything that we were talking about, epsilon and chi, that were our predictions right?
Epsilon seems to be also quite strong. 100 meters. Deep. Which we didn't predict.
Yeah. I don't think that there's any way that you could have predicted this banded structure without looking at the shear first. So that's okay that you didn't see that. Any observations? I accept answers from the peanut gallery as well.
Where you say that shear is, would have been useful to understand the banded structure, but the banded structure does follow the isopycnals roughly. And those two do go together. So that's another thing. You see where the isopycnals are far apart. That's the quiescent area, but not a whole lot of stuff going on. The black blob in chi and the dark blob in epsilon as well on the top left of the plot. Whereas, yeah, where you have isopycnals close together, you would expect to have more stuff happening. And those isopycnals, that's what we talk about when we talk about stratification, right? Which is another word that gets thrown around that you're gonna, yeah, you know, in this soup of words that we're using, yes.
So I will agree with all of that and I will modify it just slightly. In that this blob right here where the isopycnals are separated is kind of where the core of the Gulf Stream is. So while we don't have a lot of density structure going on, we do have strong velocity. So this is one of the cases that we've been harping on a lot this week of like, you do see a higher epsilon that is not associated with high chi there. So this is an area where the isopycnals are far apart, there's no stratification, it's already well mixed. It's like within the Gulf Stream, it's been trucking along in the Gulf Stream, and there aren't any gradients left to dissipate. So this is an example of somewhere where we have epsilon, kind of, I mean, not as high as down here, but we have some epsilon, and we have not as much chi. I thought that was kind of cool. Yeah.
We also have high in the like surface there, but not really strong stratification.
Right here.
Yeah, like that.
Yeah.
Blob. Yeah, can you explain that a bit?
I think what I would say about that would be that you also have stronger currents there. So even though you don't have as much stratification, chi is like, because you have more overturning more currents, perhaps, even though you don't have as much stratification, the dissipation of temperature gradients is still strong. So like if you want to compare like the magnitude of chi down here to the magnitude of chi up here, you need like mechanical mixing as well as temperature gradients. So perhaps up here you have more mechanical mixing.
So that, maybe I misunderstand.
No,
Does that kind of contradictory to what you just said about the blob? Because in the blob, you also have high like currents, but not aligned high.
Yeah. I don't know if I have the best answer for that right now. About like this, so I think what Keely's getting at is the difference between this section right here compared to this one right here. Like where you have further apart isopycnals, but still a big, yeah.
Yeah, well, there's
That's a good
one thing you
observation.
can see too, and that is typically that the closer we move to the surface, the more things are generally going on, because you have diurnal cycles of heat, and you have like, yeah, more surface currents, and like things are churned and mixed, and if you had some sort of wind put energy into the ocean, that would show up there first. So generally, yeah, upper ocean it's a cool place, but it's typically a bit more complex than when you dive down below 200, 250 meters, where things have sort of like settled out a little bit. Another thought.
The other thing that I know about this data set that I didn't tell you is that there's a little bit of a warm core eddy just north of the Gulf Stream here. So that might be a reason why the isopycnals are slightly depressed here, because you have downwelling. And that could also be playing into the relationship between chi and epsilon there.
Thank you.
Yeah, thank you, Andrea.
What if the variables were measurement? They were measurement, I guess, and that's on the cut. So my question is, if you want to expect epsilon from chi, could be look similar to one that is measured?
Yes, so this data was taken with the epsilometer. So this data is from a shear probe, and this is from FPO7 fast thermistor. So we don't necessarily have to do that whole dance with using the relationship between epsilon and chi. But one of my projects at the moment is trying to use this epsilometer data where we confidently have fully defined epsilon and chi to investigate that relationship. So like one thing I'll be looking for in that analysis is like where I was asking you where are these assumptions violated. So I would expect in this area where we're seeing salinity, we're seeing the importance of salinity, I would expect that relationship between epsilon and chi to not give as good of an answer. So that's one of the things that I'm still trying to parse out in my research is like, where can we use that relationship between epsilon and chi and where can we not? And how can we relate it to our assumptions?
Because I don't know if the unexpected or our epsilon calculator from chi can reflect the current behavior, because in this case we have high epsilon values into the current, but we don't have that behavior in chi. So if you expect if you calculate epsilon from chi, can you see this behavior?
My guess would be no.
Yeah,
I haven't done it with this transect yet, but yeah,
so
that would.
it's part of that.
Yeah, no, so if we go back to this, so like we can only use this relationship where there's mechanical turbulence mixing away density gradients that are only defined by temperature. So if salinity is important, if there's no temperature gradients being mixed away, if that mixing, so a big thing that we're leaning on here is this mixing efficiency, which we assume is 0.2 in the ocean in a lot of cases, but then there's so many studies of when it's not 0.2. So if you don't have a constant mixing efficiency, or or if it's not what you said it was, then this whole thing falls apart.
Or if you have double diffusion.
Exactly. Yeah, so we'll actually, tomorrow, we're gonna talk about some complicating factors. So Leo Middleton is gonna come in and talk about double diffusion, and I'm gonna dig deeper into some of these assumptions and when they're violated. Yeah. But I think we should probably break for lunch now, unless anyone, maybe you can find me after, there's more.
Right, and then right after lunch, we have a little lab tour, which that one pretty soon.
That's in the main lab, so I
Okay.
think we should just meet here.
Yeah, let's just meet outside, like right out here at a couple of minutes before 1, like say 12:55 or something. And we'll hear from Matthew Alford on the history of the epsilometer. It's gonna be great. You get to look at some actual things. It's gonna be cool.
And for folks on Zoom, we will try our best to have the owl and set that up. This one might be a little bit difficult to see a lot of the demonstration, but we'll try and set that up.
Yeah.
Be able to see.
A lot of what Matthew has is slides, so it
Well,
would
yeah.
still be worth showing up for that
Yeah.
part if you want.
All good. All right. 12:55, just outside here, and then we'll take over the lab. Okay.
You're